As we get to chapter 14, I thought it'd be fun to introduce you to a sports statistic that is rather interesting. And to get there, let's first talk about flipping the coin. Suppose you toss a coin, you get 8 consecutive tails. What would be the probability of getting a tail the next time? The answer, it's a half. 50%, just like all the other tosses. The fact you've gotten 8 tails in a row doesn't necessarily mean that you're due for a head, which is what a lot of people say. I'm due for a head. Now, granted, it is very, very small probability of getting 8 tails in a row, but it is possible. Once it has happened, though, the probability of a 9th tail is still 50%. Same thing goes for baseball. You've heard the announcer say the batter is struck out 10 times in a row and he's due for a hit. It's the same fallacy. Each at-bat is an independent trial. Now, granted, if someone did strike out 10 times in a row, possibly they're quite nervous at the plate, and you might say that it's not an independent event, but we're going to get to that in a second. The probability of a hit should be the same as before. If the batter is striking out a lot, possibly there should be a discussion with the batting coach. This is what I wanted to get to. This is a rather interesting study, which was done by these people as far as to examine the hot hand myth in professional basketball. Hot hand means you've often heard the phrase, get the ball to so-and-so. He or she has a hot hand. They're hitting right now. And you want to feed them the ball because they're hot right now and they're hitting everything they throw up. These researchers examined film from all NBA shooting contests from 94 through 97. They wanted to try to find out to see if there was sequential dependency within each shooter across all shots. In other words, do they make shots in a row? Do they have a hot hand? And what they did was they characterized a run as one or more hits and misses. Thus, the sequence hit, 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 hit is just one run. There's no change. One run. Here, look at this one. Hit, 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 miss, hit. That has 3 runs because the first hits, then this miss, and then the hit. Okay, so there's 3 runs. Now, if the hot hand theory is really correct, if it's true, a player should have few runs, okay? And their hits and misses should be in clusters. But in the research, what they did was they found that only 2 players had a significantly smaller amount of runs than expected by mere chance. Half of the shooters had fewer runs, half of the shooters had more runs. Okay? They compared shooters' hits and misses. The data were more in accordance with chance than the hot hand. Through their analysis, the conclusion was drawn there is nothing supporting a hot hand hypothesis, which I think kind of interesting. Coaches and fans alike always say, feed so-and-so the ball. She has a hot hand. Here's what is really interesting, though, and this makes perfect sense. They analyzed all free throws, foul shots, okay? Free throws or foul shots in all 5 regular seasons from 2005 to 2010. There was a significant increase in players' probability of hitting the second shot in a 2-shot free throw compared to the first one. They also found that in a set of 2 consecutive shots, the probability of hitting the second is greater following a hit than following a miss, which makes sense. You're warmed up on the first one, right? And you should. So there's 2 conclusions they've made here. There is dependency when you're doing free throws, okay? There is significant increase in probability of hitting the second one, and even more so when you made the first one. Kind of interesting sports statistic. Oh, what is this? Well, in chapter 14, we are going to be talking about graphing once again, graphing lines and so on. And here's one of my favorite lines. As the amount of bacon eaten increases, your enjoyment goes up. Positive correlation to eating bacon. All right, so let's get into 14.1. Now, chapter 14 is the last topics that we are going to do in this course. We'll do 14.1 today, and 14.2 we'll do next time. So let's talk a little bit about linear equations, okay? Linear equations have graphs that are straight line. The lines can be vertical lines, horizontal lines, or what I call slanted lines like this one, okay? Slanted lines have equations y equals mx plus b. You probably all remember that phrase from back in your days in Algebra 1, back in 8th and 9th grade. Y equals mx plus b is the standard equation of a slanted line, okay? Or as the author of your statistics textbook does, he does not use m for slope and b for the y-intercept. He uses b1 for the slope of the line, and the b is where the line hits the y-axis. He uses b sub 0 or b naught for the y-intercept, okay? So here the equation of this line. Now this, I hope you can see this. The equation of this line, notice it hits the y-intercept, or where it hits the y-axis is 1. So there's a 1 there. And the slope of this line is up 2 and over 1, up 2 and over 1, up 2 and over 1. It's 2 over 1, which is the slope of 2. Okay, so the equation of this line is y equals 2x plus 1. What I really want you to understand about equations of lines is not really necessarily the algebra involved here, but what happens for each increase of x of 1. As x goes to the right, 1 unit over, do you see the y's go up 2? For each increase of x, the y's go up 2, okay? Works in the positive slopes. It also works in the negative slopes. For each increase of x in negative slopes, it would go down by a certain amount. All right? That is where we're headed with the business applications of these linear equations. Okay? But not all lines are slanted. Here's a coordinate plane. This line you can see is down 2 below the x-axis. Every point on this line has a y value of -2. The equation of this line is y equals -2. Here's a vertical line in blue, okay? You can see that it's over 5. No matter what you do, you're over 5, okay? Continuing on forever in both directions, the equation of that line would be x equals 5. Although we are not going to do too much with horizontal and vertical lines. All of our lines will be slanted lines. All right, and what I'm talking about, as far as what I want you to be able to do with lines, Susquehanna Plumbing charges $55 for a service call and $40 per hour. Write the equation of this. So what we have is a cost, or the y value will be the cost, total cost of a visit by the plumber, okay? They're going to charge you $55 just to pour in the driveway. With no hours at all, your charge is $55. So when x is 0, okay, when x is 0 on that coordinate plane, you're getting a $55 charge, all right? That's where it hits the y-axis, 55. Now, for each hour that you have the plumber at your house, you're charged $40. So the equation here is 40x plus 55. Let's sketch a graph. To sketch a graph of this, what we could do, because it starts at 55, is do this, put a squiggle in there to show there's a break. And then we could go, for instance, 50 and 60, 70, 80, 90, and so on, okay? We know that when they pull in your driveway, okay, you're being charged $50, okay? Then for 1 hour, here's 1 hour, you're being charged $40 extra, 40 plus 55, pardon me, 55, not 50. Okay, so here we are at 55. Then we're up at 95 right up here. Okay, I should probably have made the y-axis longer. But after 2 hours, you're up at 135, which would be 100, 110, 120, 130, 135. So we're over here, about here. And here we have the equation graph, okay, of Susquehanna plumbing. All right, this is a positive slope. It is up 40 and over 1. All right, for each increase of an hour, your bill goes up $40. For each increase of an hour, your bill goes up $40. For each increase of an hour, your bill goes up $40. Okay, this is a positive correlation because as this one goes up, this one goes up. Hours go up, cost goes up. Okay. All right, so that's Susquehanna plumbing. All right, a tree has 250,000 leaves and loses 3,000 leaves per hour. Okay, write the equation. Y could be the amount of leaves at any particular time. It starts out with 250,000 leaves when the time starts at 0 hours at the very beginning, just like Susquehanna plumbing. When they pull in your driveway, they're charging you 55. At the beginning of our experiment, there are 250,000 leaves. Okay, so before anything starts, it's 250,000 leaves, and we know it loses negative 3,000 per hour. X is the hours, Y is the number of leaves remaining. Find how many leaves are present after 10 hours. You put 10 in there. 10 times 3,000 is 30,000. Subtract 30,000 from that, and we would have after 10 hours, there would be 220,000 leaves. Okay? This is a negative slope because the amount of leaves on the tree just decreases as time goes on. Okay? Negative correlation because as time increases, the number of leaves go down. How about in this one down here? Correlation, it's a positive 3. As X goes up, like when X is 0, Y is 7. When X is 1, Y is 10. As X goes up, Y goes up. This would also be a positive correlation. The change in Y for each increase of X of 1, for each increase of 1, the Y's are going to go up 3. Okay? All pretty easy stuff here. During World War I, it was discovered there was a relationship between the length of a person's ulna, which is the thinner arm and the thinner forearm bone, and their height. Okay, the height of a male was found to be this times the ulna, plus 85.61. This is all in centimeters. The height of a female is this times the ulna, plus 85.80 centimeters. Okay? Just like we were talking about, these are linear equations. This is positive correlation because as your ulna length increases, your height increases in both situations. Positive. Okay? Skeletal remains of a man are found. His ulna measures 21.5. What is his height? We're going to take 3.16 times 21.5, get your answer, and add on 85.61. And what I get is, the height of the man is 153.55 if you're working along, okay? A woman whose height is 143, this is the height, not the ulna. So you must put the 143 is equal to 2.97 length of the ulna plus 85.8. We can subtract 85.8 And I get 143 minus 85.8 is 57.2 is 2.97 times the ulna. Now divide 2.97, and I get her ulna length is 19.26. Okay? Everybody with me so far? Really not tough. All right, let's talk again, a little bit again about positive and negative correlation. I've got a few examples there. How about, for instance, beer drinking versus dexterity? I mean, the more beer you drink, the clumsier you're going to get. Your ability to do things with your hands or to walk is going to become compromised. This should be negative correlation. Beer drinking goes up, dexterity goes down. Hours studying versus your GPA, your grade point average. Hopefully, the more you study, the more your GPA goes up. Positive correlation. Sun exposure versus skin cancer. More sun exposure in most cases, it goes up. Okay, the amount of skin cancer is also going to go up. Positive correlation. Weight versus hair color, no correlation. Okay, no correlation whatsoever. Many relationships are not necessarily linear. There's a very famous one that we're going to work with a little bit. It's Newton's law of cooling, which states that the longer a heated object is in a room, the more the object will approach the temperature of the room. In other words, supposing you have a very hot cup of coffee, okay, at a certain time t equals 0, when the experiment starts, your coffee might be up here at 200 degrees. All right, you take that cup of coffee and set it on a table, it immediately starts cooling. Now, initially, it cools pretty rapidly, very rapidly. But as it gets closer and closer to room temperature, and we can kind of dot that in here. Suppose this is room temperature at 70 degrees, okay? What's going to happen? It's going to slow down and eventually hit room temperature and stay at room temperature, okay? So Newton's law of cooling is a very fascinating thing, and there's actually, Isaac Newton came up with an equation to actually calculate the temperature of that cup of coffee while it is decreasing. Here is his law of cooling, okay? You will probably, no, you undoubtedly have a problem on Newton's law of cooling on the test on this material. But I will give you the law of cooling. You don't need to memorize this. You just need to know how to work it, all right? So let's talk about this. The temperature of the object, like a cup of coffee, is equal to T sub S. This is the temperature of your surroundings, T sub S, plus D naught. D sub 0 is the initial temperature difference between your item and the room. So this is the temperature of the surroundings, 70 degrees, okay? D sub naught is the initial temperature difference. The difference between these two would be 130 degrees, yep. K is a constant. A cup of coffee would have a certain value, a constant that goes along with coffee, because of the nature of what coffee is and how quickly it loses heat, okay? A cup of coffee may lose heat a lot more quickly than a cup of steel, like it's steel or some mineral, all right? Different objects have different constants that would go in there, and you'll always be told that in the problem. T is the amount of time, and sometimes time can be stated in hours or minutes dependent upon your constant, whether it's worked out in minutes or in hours, okay? So let's do a problem. Let's go back to the formula, which is the temperature of the object is equal to the temperature of your surroundings, D naught, temperature difference, e to the kt. One other comment. There is that number e again. Do you remember back when we started talking about normal curves, and I gave you a formula to calculate the height of a curve? And I said it's that wonderful mystical number e, which is 2.718, goes on and on and on forever, never stops, never repeats. There it is again, in the temperature of a cooling object. Ah, it's a great number. Okay, so anyway, let's do the problem. Here we have a freshly brewed cup of coffee. K is negative. Sorry, the negative sign's up there. Negative 0.05, and this K value is evaluated in minutes, okay? The coffee was 190 degrees initially. The room is 72. What is the temperature of the coffee at 9:30? All right, so here we go. We want to find this, the temperature of the room, or the temperature of the coffee at 9:30. The temperature of the surroundings is 72. The initial temperature difference, I think, is 118. Okay, E, the constant, is negative 0.05 times the time, because it's in minutes. Don't put a half in there. It's 30 minutes. Okay, so work this out, and we have 72 plus 118 times, get your second function ln. Remember that from the last time? Second function ln, I'll put an e on your screen, raised to the negative 0.05 times 30. Close your parentheses, and I get 98.3. Okay? The temperature of the coffee will be 98.3 degrees. Okay? All right, and remember, Newton's law on cooling, it is a negative correlation. The more time you go up, the less temperature you have, but it is not linear. This is not linear, it's curled to start. But you should be able to do linear problems. How about this one? Nifty Nissan sells a new Versa for $13,500. So when it's brand new, not even off the lot, when time t equals 0, at t equals 0, we're up here at $13,500. That's the cost of the Versa. It depreciates at $1,200 per year. So we could go down here to $12,500, $11,500, $10,500, and so on. Okay? So write the equation that gives the worth of the car as a function of time. So the worth of the car, Y, will be equal to, it loses $1,200 per year. Negative correlation, negative slope, so it's going to lose $1,200. X is your time in years, and it started out at $13,500. Okay? Find the worth after 5 years, you put 5 in here, times this is negative 6,000, becomes 6 off of that is 7,500, and you'd have to keep going down here. And possibly I should have rescaled this to make it a little bit better. Let me do that. Sorry about that. Let's do this. Okay, so here we have these are going to be done in thousands. So here we have 1 and 2 and 3 and 4 and 5, 6,000 and 7 and 8 and 9 and 10 and 11 and 12 and 13. Okay, so it starts up here at 13,500. Okay, in 5 years, 1, 2, 3, 4, and 5. Here are the years. These are in thousands. The worth of the car starts up there. And in 5 years, we're at 7,500, which is going to be pretty close to being right about there. Okay? This starts and is going to come down like that. Okay? Back to Newton's law of cooling. Do another one of these. We've all watched CSI programs on TV or seen it in the movies where the detectives come in and they do all kinds of calculations and they say, I think the victim was murdered 3 hours ago, right? How do they do that? Newton's law of cooling. That's how they do that, which was the temperature is equal to the temperature of the surroundings, initial temperature difference, E to the KT. All right, forensic team arrives at the scene of the crime. They determined the surrounding temperature was 70. K is negative. There's the negative sign over there again. How does that happen? Negative 0.195, and this time it's figured out in hours, okay? So what about the temperature difference? If the surrounding temperature is 70, the initial temperature difference when the person was murdered, his temperature was 98.6. If the room is 70, the initial temperature difference is 28.6. Yeah? E to the negative 0.195 times 5. So what should the temperature of the victim be in 5 hours? We can figure that out. 70 plus 28.6 times second function ln to get your E, raised to the negative 0.195 times 5 hours, and I get the temperature of the victim should be 80.78 degrees in 5 hours. Okay? All right, homework. You've got a couple extra problems here. All right, Allna's, Newton's law of cooling, and then there's some textbook problems down here. You will also be doing some graphing. Okay, you're going to have to get yourself some graph paper to make nice, accurate graphs.